No, it's really great fun to be back here and seeing so many friends from the university, from HITS, so many faces. And I must say, you all stayed the same. You stayed young, despite not having, been 5 years away. So this is amazing. And so congrats to that. And congrats to this really lively scientific institute, lively as ever and more successful than ever. I'm really impressed. And I'm also thankful that I have the opportunity now to talk today about my research. And I gave this somewhat technical title, Interfacing Galaxy Formation with Precision Cosmology. And I would like to give you a flavor of what this scientific field does in trying to predict basically the formation of galaxies from a theoretical angle, and then also making predictions that are needed to understand some of the deepest puzzles in our universe, namely the basic fabric it is made of course, of dark matter and dark energy. Many of you will have heard of that, not only the astronomers, of course. And, just to give this away, this is, of course, a deep puzzle, and there are various observational missions underway, large mega surveys of galaxies, and we need also theoretical work to support that. And I will basically tell you today about that effort. Now, let me maybe start with this introductory slide, which is showing you one of the most important observations that we have about the young universe. That's here on the left. This is a picture showing the universe when it was 380,000 years old, the so-called microwave background fluctuations, or the microwave background radiation. And the fluctuations you see here as these little, these speckles and ripples in this map. And these are tiny temperature fluctuations around a mean temperature today of 2.73 Kelvin. And the amplitude of these fluctuations is actually really tiny, 1/10,000th or so of the mean temperature. So we have a picture of the baby universe, and that picture tells us a whole lot. It shows us that the universe was very simple and smooth at the time. It did not contain stars nor galaxies, and probably also not supermassive black holes either. And since then, the linear dimension of the universe expanded by about a factor of 1,000. So the volume blew up by a factor of 1 billion that you see in this trumpet shape here on the right, which is kind of a cartoon that shows the expansion of the universe that lasts until today. And this expansion was accompanied by structure formation. Out of this cosmic soup of matter and radiation, some galaxies started to grow and became bigger with time. And that's the process we'd like to understand. We would like to understand when this happened, why it happened in certain places, why the galaxies have certain sizes. A galaxy, of course, is a metropolis of 100 million stars or so, or more than 10 billion in our Milky Way. And these large agglomeration of stars we call galaxies. And of these galaxies, we see billions in the universe today. So the universe today is very different from how it used to be, right? It's very structured. It completely changed over 13.5 billion years of cosmic evolution. And that's essentially the process we try to understand in more detail in physical cosmology. And in this cartoon picture, you see a few more things. I mean, first of all, you see, the Big Bang, sketched here as quantum fluctuations. We think that there was an inflationary epoch at the early times, setting the stage, so to speak, producing a few minutes after the Big Bang also the light elements, helium and hydrogen. That's the Big Bang nucleosynthesis. These are processes we understand very well. What you don't know is what caused the Big Bang. So don't ask me that. There are speculative theories about this too. But we do understand the evolution fairly well over much of this long time scale. And we know the initial conditions, which you see here on the left on this green surface. This is again the microwave background. After that, you had a period of dark ages where no stars yet were lit up. The universe was a dark place. Eventually, the first stars ignited and then quickly built up the first galaxies. These are process that we now start to observe more or less directly with the James Webb Space Telescope, and I'll come back to this later. And today, the universe became bigger and thinner. The mean density has dropped a lot. And in this trumpet shape, you see another interesting thing. The acceleration recently, in the last 5 billion years, actually picked up in speed. There's an accelerated expansion today, which is caused by an anti-gravity, which we call dark energy. what this really is, we don't quite know, but it's in our theories, it's also in our simulations. Okay, with that, introduction into this, I will come to, the concept now that we have in computational cosmology is that we take this initial state here that we observe with high accuracy and initialize it on a computer, and then do this evolution forward in time. We evolve the laws of physics, trying to see how this universe on the computer evolves. And I will show you many results today that exactly follow that concept. They start basically at this microwave background radiation when the universe became neutral, and then evolve that simple state forward in time and develop all the complexity that we see today. Now, but there's another strange thing in the universe, namely that it's actually filled with another mysterious substance, not only dark energy, but there is actually dark matter. Dark matter is a component that's made out of really particles. We don't know what the particle really is. We think it's an elementary particle not contained in the standard model of particle physics. So there are various candidates for that. I don't really talk in detail today about the various scenarios for that. But we are convinced in astrophysics that there is dark matter. We see its action everywhere we look in the universe. We see its gravitational pull in galaxies, in galaxy clusters, its gravitational pull in structure formation. And via that observation, we infer that there must be mass creating that gravitational pull. And that's the dark matter. What you see here is a simulation of basically the dark matter distribution today that's predicted by models that follow this strange universe forward in time, predicted in the Milky Way galaxy. This is how we think that dark matter should be distributed in our own galaxy, right? Unfortunately, it's dark and it's not as nice and luminous. We can't see it. We can see it on the computer. We can paint it in various colors and then highlight that way the lumpiness, for example, that we are predicting for the dark matter substructure. So that's something we can, for more than 2 decades, can compute forward in time really well. The dark matter component of the universe, the reason why this is easily computable is because these dark matter particles only feel the gravitational force. In particular, they stream through this room here. They don't really interact with much of us. They just stream through the Earth because they only see the collective gravitational field in the galaxy and in the solar system. And the same holds true for us. So the interaction is basically so weak that by all standards, it can be neglected. Maybe there are residual weak interactions, but they can be neglected. And so they only follow gravity. So I'm just showing this because I want to get to the main topic of my talk. I just want to remind you of this, that we'll come a little bit into the background, that the dark matter contribution in the universe is actually dominating the gravitational force. 85% of the matter is dark matter. And so if you want to compute the gravity in the universe, you basically have to first of all consider the dark matter. And the dark matter is, for example, neutrino particle. This is still the favorite candidate, where these particles would have the mass roughly of 100 times the mass of a proton or so. That is at least for a long time the leading candidate. One hasn't really found this particle in direct detection experiments so far. That's why it has become a little bit unpopular, and one is a little bit nervous now whether this is really the correct candidate. But here I want to just show you that it's actually possible to predict the entire hierarchy of cosmic structure if the dark matter is indeed made up of such particles. So here's a so-called zoom simulation that looks into a large patch of the universe, which here is about 500 million light years across. And in this little circle, the calculation zoomed in, and in all of these subsequent calculations zoomed into the region by large zoom factors until we find the smallest dark matter halos that are expected to exist. They are roughly of the mass of the Earth. And the reason why there's no smaller things has to do now with the particle physics properties of this particle. It's a warm neutrino particle, and it has some residual thermal motion that prevents it from making still smaller little pebbles. But this is something we can predict through computational means, and it's not possible to predict this through analytic computation because of the the complexity of the structures involved. And we basically are able to resolve the full hierarchy of all the structures over 30 orders of magnitude that are supposed to exist in a universe dominated by dark matter. But I don't really want to talk about the dark matter. I want to talk about galaxies, the luminous part of the universe, right? Exactly the part that we see that's not made out of dark matter. And here you have this cake diagram, right? This shows the energy content of the universe today, as we expected in the leading cosmological theory, lambda CDM. And in this cake, you have two big pieces today. One is the dark matter. This is this elementary particle that we don't quite know what it is, but we can actually simulate its properties fairly well. And then we have 3/4 is this dark energy. This is the anti-gravity that's producing the accelerated expansion today. In the standard cosmological model, this is represented by a cosmological constant that Albert Einstein proposed already in his famous theory of general relativity. In that case, it is just a constant in the theory of general relativity. Again, we have the problem that we don't quite know why it should be there. So the theoretical physicists would like to find a more natural explanation for this. And the other explanations, the more general ones, are called dark energy. So the cosmological constant is basically a special case of a dark energy field. And there have been recent indications now for the first time that people in the field are very excited about that. Maybe indeed experiments have been able to show that deviations from a cosmological constant, which would be, if confirmed, a real hint that the dark sector is more complex and it's not a cosmological constant. And there's a certain degree of hope in theoretical physics that that will turn out to be true, because it would be very interesting. But the yellow part here, this is the ordinary matter. This is helium and hydrogen gas with just 1 or 2%, about 2% today of heavier elements. So most of the stuff in the universe is really quite boring, right? It's helium and hydrogen. In fact, hydrogen is 74% of that, and helium is about 1/4. And then there's just a tiny mixture of 1 to 2% of so-called heavy elements that have been synthesized in stars and in neutron star collisions, etc. And we are really stardust, as I'm sure you learned at HITS a lot from our stellar colleagues. So stars produce these heavy elements, but they are, cosmologically speaking, just a tiny icing on the cake, right? So the stars make up only 0.5% or so of the cosmic energy density. They are not particularly important. Planets far less, right? So planets are, and we are completely unimportant in terms of the energy density of the universe, right? So if you could remove all the planets from the universe at large would still evolve the same way, right? So this is not important. And the black holes, I get back to those, they are only about 1,000th or so of the mass of all the stars. So they are, of course, super interesting, but they are not dominating the energy budget in any way. But they are one of the most powerful engines that we have in the universe. In fact, the energy produced by the stars equals roughly all the energy produced by the black holes together over the history of the universe. They're very closely similar. That's actually the reason why both of these components can influence the evolution and the formation of galaxies very importantly. So that is a basic, these are two basic players. We call these so-called feedback processes, that namely the energy produced by stars and the energy produced by growing black holes influences the formation of galaxies in important ways. Now, I said that we initialize this state in a computer, and then the idea of the research we're doing is essentially to do an evolutionary calculation forward in time over 13 billion years. So we number crunch the laws of physics forward in time. Those are partial differential equations that I'm not bothering to write down now in this talk, but they are well known. This is mostly classical physics, except that you have to put this into an expanding space-time. And it's combining aspects of gravity, of hydrodynamic, of atomic radiative processes, and then processes that are not so well understood that have to do with star formation that we are approximating in our calculations. And besides a computer, you also need numerical techniques. So that is where the researchers in this field spend a lot of effort on and trying to devise basically actually codes that can execute the that can leverage the power of these parallel machines to evolve now, for example, a fluid forward in time. And we have developed methods called ARIPO for the purpose of galaxy formation calculations. And this is a bit special in the sense that it's using a mesh that you see illustrated in this little movie. And this mesh is dynamic. It can move with the flow. And that's special. There are well-established techniques. Normally, when you want to simulate hydrodynamical flows, you use a grid, a mesh, often a Cartesian mesh, or another type of fixed mesh geometry, and you then compute how the flow evolves over the interfaces of this mesh. Now, our mesh is moving along with the flow. The red points that you see are so-called mesh-generating points. The cells that are moving here are so-called Voronoi cells. This is a mathematical construction where for a given set of points, you define the region closer to a given point than to any other point as its Voronoi cell. And these mesh-generating points create the mesh, and they move with the speed of the local flow. And for us in galaxy formation, this has a number of advantages because you obtain with this a mesh that's following the geometry of the object you have in under study. The method that's making it into a galaxy has to be pulled together from a large region in space. And as it's pulled together, the mesh-generating points are also getting closer, and then the mesh resolution automatically becomes better. That's the main advantage. And another is that the gas flows in, for example, here's a differentially rotating model for a galactic disk, of course, in very low resolution so that you can appreciate the concept here. But in reality, this gas rotates around here, around the center on a centrifugally supported orbit. And the pressure in this gas is actually very low. It's fairly cold. And the pressure forces are much smaller than the gravitational forces. And the speed with which this gas circles around is far larger than the sound speed of the gas. And in this case, traditional methods, they have very large advection errors. And these we can absorb in this method. So that's a fairly technical point. But it proved very important for some of the advances in the field that we were able to make over the past, say, 15 years or so. That technique was quite instrumental for that. In fact, still the leading simulations, I would say, of galaxy formation in the field are called Elastis-TNG. This was a project that was just coming out when I'm actually moved from HITS to Garching. So this was largely still devised here at HITS. Actually, we were sitting over there on the roof terrace and on the terrace and brainstormed for many Sundays. So my collaborators from the US, they typically came on weekends, and we actually worked here on weekends to devise that simulation set. And it proved to be very successful. So we have done 3 simulation boxes, TNG 50, 100, and 300 in different volumes. Reason for this was we always have to simulate a large periodic cubic region of the virtual universe. And we only can afford maybe, about 20 billion resolution elements. And so when you simulate a larger volume, you then have poorer spatial resolution and vice versa. And so by stacking these 3 boxes together, we could then cover a wider dynamic range. And here I give you a visual impression of how such calculations look like. This is a zoom into the dark matter distribution. You have the so-called filamentary cosmic large-scale structure. But in these hydrodynamic simulations, we can also visualize the gas. So this is now the intergalactic medium helium hydrogen gas today that's hot. It's ionized by the radiation field, by the stars, the UV radiation. Now we see the metals, so the heavy elements that have been synthesized by stars in galaxies and blown out by winds from galaxies. In fact, the galaxies, they come now in view. In these simulations, when you now zoom in into these dark matter halos at their centers, you actually discover stellar systems. And this is a rotationally supported disk galaxy, which is relatively bluish because it still has ongoing star formation. There are young stars in it. They have a blue color, and while the old stars have redder colors. Here you see, for example, the gas density in white. Here is the interstellar medium that's still star forming. And we zoom back out into the cosmic large-scale structure. And here now these galaxies are already tiny, tiny points, right? But you have millions of them here in this calculation. And you also have here in the velocity field, big bubbles, for example. This is the impact of supermassive black holes that have blown out a lot of gas into the intergalactic medium and produced shocks. And here at the end, we see the dark matter. That's fairly regular. The gravity can only pull dark matter together. It's a one-way street in a way, while the baryonic physical processes, there galaxies can spit out material again that you have seen in this wind and this bubble around a star-forming galaxy. Now, the galaxy I just showed you here on the left, this was from illustrious GNG 100 calculation. This is sort of the quality that you get out of for this intermediate resolution. On the other galaxy on top is from TNG 50, where we have higher resolution. You see what difference this makes, right? With the higher resolution, you can see the spiral arms, for example, in more detail. And on the right, and that's not a simulated galaxy, this is Andromeda, right? So that's how real galaxies look like. And, you know, our galaxies are not as pretty as the real ones so far, but we are getting there. I think so. We are having, and that's now the interesting thing. Of course, once you simulated the universe and produced all of these many galaxies in one large cosmological volume, you can now compare to observations, trying to understand whether these predictions make any sense or not. And that's what has been extensively done. And you know, you're not only having this one galaxy, but you literally have thousands and tens of thousands, hundreds of thousands predicted in all variety of their shapes and sizes. Galaxies come in different varieties. They are disk galaxies, they are spheroidal galaxies. Some have bars, some have spiral arms, some are train wrecks. They have irregular galaxies, so they come in different sizes. And so what we then do in much of our work is to trying to interpret what we have simulated, whether that compares to observations, how well it compares, and from the discrepancies, we're trying to understand whether our physical models are to be blamed, or maybe it's numerical inaccuracies, right? These are always a bit degenerate, these two things, and we have to try find out what the real cause for any discrepancies is. Now, before moving on, I just want to give you a flavor of that, and that's maybe one of the stunning things is that these galaxy formation simulations, after having sort of 15 years ago, there was a bit of an impasse in the field that many of the calculations have failed to produce sensible galaxies. The newer generations of simulations, illustrious TNG is an example, they are really quite successful. Here, that's more for the experts. You can, for example, compare the sizes of galaxies, right? These sizes, the radius is something as a function of their the stellar mass. This is shown here in these plots where data is compared for late type, and so for disk galaxies and for elliptical galaxies between observations and simulation, and the agreement is rather good. So the galaxies that come out, they have the right size, they have the right distribution of stellar masses and luminosities. They also have the right distribution of colors. There's a so-called bimodal color distribution. So there are basically two families of galaxies, blue ones and red ones, and the relative abundance has a systematic trend with size of galaxies. The small ones prefer to be blue. The very big ones eventually are red and dead. And that transition is also reproduced by the simulations. And I'll get to this. The key factor for this is actually the supermassive black holes. Without them, we are not able to explain that. We can also look at what's called the cosmic large-scale structure. Here in this image, you see exactly that, what we call the filamentary distribution of matter on scales of several 100 million light years across. So these are gigantic scales. But I will come to calculations that are even bigger than this later. So here you see what's called the cosmic web, filamentary distribution of matter. And at the intersections are big concentrations of matter where galaxies and also galaxy clusters are formed. And a very important test for cosmology is the pattern that's predicted here, whether the real galaxies are distributed in space in the same way as these simulations forecast. And that's something that's coming out of the cosmological initial conditions, and it's ultimately a test also of the cosmological paradigm. And interestingly, these simulations, they reproduce the so-called clustering pattern very accurately. This is shown here in these 6 panels for galaxies of different stellar mass, where the so-called two-point correlation function of galaxies is compared between the SDSS survey, this is observation data, and the simulations. So the observation data are these black points. What the simulations predict are the red lines. And you see there is a reasonably good agreement. So this has been a huge encouragement because it shows that the galaxies are actually at the right places, right? This is a non-trivial thing. It's even more non-trivial that if you separate the blue and the red galaxies, then they're also at the right places. Not perfectly so. There are some, as you see, some discrepancies. And then, of course, we have to think about what do they tell us, but they are at the level where we're thinking that we are fundamentally still on the right track. And because these simulations are so rich in the different physical quantities they predict, right? They predict basically everything that's in this. You have this artificial universe, and you can you can look at this artificial universe in many different ways. You can look at the dark matter distribution, you can look at gravitational lensing, you can examine the galaxies, their properties, you can examine large-scale clustering, you can examine the shapes and the morphology of galaxies, etc. You can look at the metal distribution, you can look at absorption line studies, and so on. And we've made the data publicly available, which was turned out to be a really smart move, because that led many people in the community to use our simulation data and do their own investigations. And they pursued many ideas we never had ourselves. And so, for LASTIS-TNG, there have been more than 860 papers written now on just this simulation project, right? This is, even though this was just a small team of 10 people doing this. And, this is in proportion to many large experiments you do, this is quite substantial impact, I would say. And, there's this postage stamp by Deutsche Post, who used one of our simulations actually in 2018 to bring out this stamp. Okay, now I'm have done enough praise of our old work. So let me come to maybe some more newer things that have happened in the past years. And I would like to talk first about this impact of the supermassive black holes and about a few surprises also, right? So it's not really the case that we know really everything that we basically put into the simulation and we can anticipate its answers. Sometimes we also expect things that we didn't quite expect. Here, for example, is an example in this time evolution on the right. This is something what we like to call an emergent phenomenon. So AGN feedback, this is a technical term, active galactic nucleus. Inside the center of every galaxy, you have a supermassive black hole lurking there. We also have one in our own galaxy, Sagittarius A star. Our own black hole is pretty lazy right now. It doesn't do much, right? It doesn't accrete much matter. It is not shining at its maximum luminosity. But if you would funnel a lot of material into the galactic center, the supermassive black hole would start swallowing that material and would encompass most of it, but 10% of the rest mass energy roughly would be released as pure energy. And this makes these black holes the most powerful engines we know, right? They can produce basically 10% of the rest mass energy they release of, as radiation, and can with that shine as a quasar. A quasar is basically as bright as 100 million stars. That's nothing else as a supermassive black hole, an AGN that's growing at the moment. So these AGN are simulated in our calculations with approximations that you can discuss, but in particular, we don't quite know what all this energy does and how it's released by the black hole, in particular how it's coupled to the surrounding gas, right? There are, for example, relativistic jets sometimes. Sometimes there are strong winds from the accretion disk. There's for sure a very intense radiation field. So we don't quite know in our simulations how we should couple this energy to the gas. And so we do something very simple. We isotropically couple it in all directions equally. But despite that, there are bimodal winds appearing by itself, right? So the energy basically goes into the path of least resistance and then creates, in, for example, this galaxy, strong bimodal winds orthogonal to the disk. This is, for example, what you see here. So there is an emergence of such phenomena, right? If you just satisfy the conservation laws, you sometimes get the correct large-scale behavior because of exactly that fact. The small-scale processes can be hidden, and you don't even have to necessarily understand them precisely, and you still get the correct large-scale outcome. At least that's what we hope. And here is an example from a paper we had in Nature a few years back about that maybe our simulations are, despite the simple model, not so wrong. This is, first of all, an observational finding, namely in SDSS, that here something having to do with disk galaxies. If you look at this galaxy, say our Milky Way is such a system, right? And our Milky Way has satellite galaxies around it, for example, the Magellanic Clouds, Fornax, and so on. And you can also observe other nearby disk galaxies with their satellite population. Then you can ask the question whether it matters where such a satellite is in relation to this disk galaxy. Basically, if you look at the orientation angle and you then ask the question whether a galaxy is quenched or not. Quenching means whether it's still, whether its star formation has been shut down or not. And then you find that that basically the galaxies are more quenched in the direction of the major axis. That is when they are here in this piece, and not so much on the minor axis, right? So now, why is that? So this is a very clear, there's a modulation here that you see a 5% modulation with this angle of orientation, right? And then we looked at this in our elastocene G galaxy population. This is in green. We find the very same modulation of that, right? And now we argued that this is because of a different distribution of the gas in these systems. Here on the top right, you have a stacked version of the gas distribution in this disk galaxy. So the disk is basically here in the horizontal plane, and where it's blue, the gas is actually overdense. The red is here underdense. That means here out in the halo, the gas is less dense up there. And that's because that's explaining why the satellites are less quenched up there, because they're experiencing less of a headwind. When they move through the galaxy, they have to move through this gas. And if there's a high gas density, then their own star formation is reduced because their own interstellar medium is stripped. So that's what we conjectured here as an explanation. And we now furthermore said this is coming from the AGN, because we can also do a simulation where we do not include black holes, right? We can test this physics. And in a simulation where we do not include black holes, unfortunately, I've deleted the slide, this modulation is not there, right? So we blamed this, for example, on the AGN feedback. That was a strong surprise to us. Or here, this was also a surprise. We also found that the magnetic fields that are amplified, so we also simulate magnetic fields, they are amplified by small-scale turbulent process in the gas. That this turbulence is a strong function of the winds that these galaxies blow out. And so it probes indirectly the physical assumptions we make about supernovae explosions and the winds that they blow. Now let me, in the last part of my talk, come, however, to much larger calculations still. And we have been doing those in particular, motivated by large mega galaxy surveys. One of them is done currently by the Euclid satellite project led by ESA. This satellite maps the sky and in exquisite detail, and it takes observations of galaxy images and redshifts basically over billions of galaxies once it's done. And it does that. One of the primary scientific targets of that mission is to actually trying to reconstruct the expansion history of the universe. This little trumpet shape that I showed you, because this anti-gravity of the dark energy, depending on how it evolves, whether the dark energy becomes maybe stronger or weaker with time, then the expansion rate of the universe will be changed. So the idea is to measure how the universe expanded at different epochs, and then you learn about this dark energy indirectly. And after all, it's the most important component in today's universe, right? So it's a fundamental issue in the universe. And however, and that will be my main point, in order to make full sense of the data, you actually need theoretical models that are equally accurate and equally good as this observation data. And that is where we need bigger simulations, a lot bigger ones. And that's where we worked on in the last couple of years on a project called Millennium TNG, which is fundamentally a follow-up from this successful Elastis TNG that I just showed you, and a much older Millennium project, which sort of was out of my postdoc times, where we only simulate the dark matter. Right now, I showed you we can now simulate everything, also the galaxies, not everything, but galaxies included. But the calculations, they are too small. A couple of 100 million light years don't cut it. For the cosmologies, you need billions of light years, right? You need gigaparsec to make measurements on the largest cosmic scales that are relevant. So we needed a bigger volume. And so what we could achieve is redoing this calculation in a 50 times bigger volume that we called fifth Millennium TNG. So similar type of code, a similar type of effort, but 15 times bigger volume, 15 times more resolution elements. And then we can also do a dark matter calculation in comparison to understand how the baryons impact the dark matter distribution. This is an important systematic in these cosmological probes. But this is still not big enough, unfortunately. What we need is really something that is 1,000 times bigger than the volume of Elastis TNG, right? And so that's beyond even current computing. Even if you put a GPU cluster, whatever, this is still too much CPU time, right? So for the moment, what we've basically done in Millennium TNG is we run these two smaller intermediate scale simulations and compared them very accurately to trying to then do a calculation with just dark matter in this 1,000 times bigger volume with more than 1 trillion particles. And then we craft the baryonic process on top of that to make these cosmological predictions. So a bit more for the experts, but that's sort of the technique. In addition, I come to this, we also simulated for the first time massive neutrinos. There's actually one part in the dark matter component where we know it's not quite dark matter or cold dark matter. There is about 1% to maybe 2% admixture of so-called hot dark matter, namely neutrinos. We know that there are a lot of neutrinos in the universe. Those are these light leptons, and they are not leptons, they are the mediators of the weak interaction, right? And the neutrinos, the three flavors, their summed masses is unknown, basically. It's known from particle physics that it can't be zero because we have so-called neutrino flavor oscillations from the sun. So the mass is non-zero, and it's very small, but we don't quite know how small it is. This is an important goal of astroparticle physics and particle physics in general, to determine this. It's also, it turns out, now a goal of cosmology, because it matters whether there are neutrinos with no mass at all, or whether then they behave like photons, or whether they have a rest mass of 100 millielectron volt summed or 300 millielectron volt. Because these rest masses here, they are right in the ballpark where the neutrinos are initially moving relativistically, but because they have a rest mass, as the universe expands, their velocity is redshifted away and they're slowing down with time. And eventually they become so slow that they feel this, the cluster, the matter distribution that we already have. And then they respond to, for example, galaxy clusters and modify their growth. That's something you can measure with cosmological observations. And then that way we can hope to detect what the neutrino mass will be. So we've done a bunch of calculations of such cosmologies. I don't want to bore you with the details, but some of them are the largest. They have more than 1 trillion particles and just 16 billion neutrino particles and so on. And they are done in a very large volume. And that allowed us to probe 3 different things for these cosmological missions. We have a very good idea of the numerical convergence, so the accuracy that we have numerically. We have a very good idea what the baryonic impact is. So the fact that 15% of the matter is ordinary matter that modifies the dark matter clustering slightly on large scales that you need to understand precisely. And we have the neutrino mass dependence. And such a thing, produce a lot of data, 3 petabyte in this case, that we have to work through. I skipped this. So then a new thing that we then also have done here is when you have such large simulations, it doesn't actually make sense anymore to output your simulated universe sort of at some given time, because you can never observe it at a given time. What you can actually observe is so-called backwards light cone, right? So if you look far away, you see a point, you see this, so you see the universe like it was a certain time in the past, right? So if you look basically because of the light travel time, right? The further you look into the past. And that means that that's the so-called light cone. There's an intimate connection between the distance and the time that has elapsed between emission of the signal and your observation today. And you can, we already saw this in the microwave background, where we look basically back to the edge of time, right? 13.5 billion years, huge distance. We look back to this last scattering surface, and that's the observable universe we have. We can't really see with optical telescopes any further, right? Because the universe is opaque behind that wall. Now, here is such a light cone. We basically sit in the middle of a gigantic sphere of stuff. That is what our simulation outputs. And it outputs this in a continuous fashion as a function of time. So we sit at the middle here and the bottom, and there's a spherical region going out to redshift 2 shown here. So this is several, I know redshift 2 is probably 8 billion years or so in the past, roughly. So it's quite a substantial fraction already of the age of the universe. And when you, this is the dark matter clustering on very large scales. And, you know, if you zoom in this tapestry, you see the familiar cosmic web. And here's, for example, some galaxy clusters are enlarged. But maybe you also appreciate is that towards the edge of this half sphere, the clustering is a bit smoother, right? I'm not sure whether you can see it, but it's a bit smoother. That's because, well, the universe wasn't as evolved yet at the time. And of course, the galaxies that you see there were also not as evolved. They were a bit different, right? They were several billion years younger, and and that's also what you see in observations, right? And the simulations, they output this directly, right? So here's the corresponding output now of the galaxies. So that's also what the simulation outputs. This is what you would really see in the large-scale clustering. If you had a huge survey, this is a diagram of the galaxy distribution on large scales. You see red and blue galaxies here in this enlargement. So that's actually what we see. We can't directly observe the dark matter. Well, through gravitational lensing, I come to this in a second. We see the galaxies as light posts on this underlying dark matter structure. Actually, this is the galaxies as we don't quite observe them. Here you see very nicely the large-scale clustering in the top right, for example. But what you actually see is this. You see the galaxies in redshift space, because the distance, observationally, you infer from the spectroscopic redshift. But the so-called peculiar motions in galaxies, Doppler effect comes on top of that. So there are two contributions to this gravitational, to this redshift. One is just due to the expansion of space between the emission and the reception of the photons, and the second contribution is the peculiar motion of galaxies, and that creates in these galaxy clusters these stripes that point towards us. That's called the finger of God effect, because you, in all directions, you see these structures pointing towards us. That's because of the line of sight, of course. Every other observer would see it in pointing towards them, right? So it's not particularly special for our location, but we see that. And these redshift space distortions, how they're called, they in themselves are an important probe of how the universe evolves in time. This is now for the experts, for example, this is the clustering that can measure with such calculations, two-point galaxy correlation function now in so-called light cone outputs that are directly mapping what the observers will also see. And you see here at 150 megaparsec, it's a famous baryonic acoustic oscillation peak, because this is basically a standard ruler that also tells us if we can measure that scale at different epochs, we can see how the universe expanded over time. On the right, it's measuring these redshift space distortions in the monopole, quadrupole, and hexadecapole moment of these clustering patterns. And there you see data in red in symbols, and the simulations that we have are the lines, actually. You see again that these large models, to zeroth order, they reproduce the observations pretty well, right? We are actually looking for 1% deviations between the observations and the theory. That's the level of precision that's needed to understand these cosmological effects. And because talking about 1%, here is now another light cone that shows the neutrinos. That's one of the things that are particularly fascinating us. Here on you see again a light cone, the scale here 0. We are basically in the middle of this violet dark matter distribution in the middle. On top, you see the neutrino density distribution. And also to the left and to the right, we're looking out about 5,000 megaparsec out to redshift 2. This, again, the path backwards light cone. What you see in the neutrino density field above is a rather pronounced change in the structuring, right? First of all, it's blurry because the neutrinos are, all even today, are still moving with very high velocities. They are only captured by the biggest large-scale clusters. And that's, for example, enlarged here in red. So, but on redshift 2, even these clusters would be not massive enough because the neutrinos are still much faster then. So they are responding to the structures today. And when they do, they start clumping in big galaxy clusters, and then they modify the growth rate of these structures. And that's something we can detect. And with that, we hope to constrain the neutrinos. Here's a diagram showing the impact on the matter power spectrum from the neutrinos. So unfortunately, this red signal here, this is for a rather strong 300 milli-electron volt. And probably the favored values of the neutrino masses are smaller. So that means we are talking only about 5% effects now that we can detect there. So it's getting hard, right? But it's not hopeless. Here is another example of this, the so-called impact on the cosmic star formation rate density. So this curve here is an important diagram. It shows basically how the density of star formation in the universe evolved over time. There was a peak at redshift about 2. This is sort of where the universe had its best time in terms of star formation. Actually, since then, you know, it's slowed down a lot, right? It's, factors of 6 or more, at least, as the star formation rate density declined. And, you know, the universe becomes an ever more boring place. This is because of the rapid expansion that has started. But the neutrinos make a difference here, as you see, especially at high redshift, right? And that's why, you know, people in the field like to look at high redshift in the childhood of galaxies, where maybe the sensitivity to these early evolution is largest. And this is also what we understand least well. Another discovery, very briefly, I want to show you from these simulations about weak lensing, weak gravitation lensing. But there is a way to detect the dark matter after all, more or less directly. Namely, it's distorting or it's bending the path of light through its gravitational effects. And here you see this on the left, there's a matter field, and here on the lower left, you see the impact of a large, massive galaxy cluster inducing so-called strong gravitational lensing effects that are readily visible, right? There are huge distortions of images. There are multiple images of some sources that are in the background by that. That's known as strong gravitational lensing. When you have that, you can make very detailed analysis of how much mass there is in this lens. What's less obvious is that there are also lens effects far away from these very massive contributions. For example, in such a field over here, because here there is still a very tiny tangential distortion on average expected of these images. So if you have a gravitational lens in the foreground, so some mass distribution, and a lot of images in the background, then the light has to go through this foreground mass distribution. And if these light are galaxy images, then they are slightly distorted in their shape. Now, the problem is, of course, these galaxies, they are more or less elliptical in their shape. You see this here in this enlargement. So they have an elliptical shape, which you can define here as source ellipticity. And this source ellipticity is distorted by the gravitational shear from this weak gravitational lensing. And now the idea of weak gravitational lensing analysis is basically to take an expectation value here of this and of this equation, and you can basically measure the observed ellipticity in a field, take the average ellipticity of that, and then you know, take the average ellipticity of the sources and of the gravitational shear. And if the galaxies are randomly oriented, then this term would be 0, right? You then measure directly the gravitational shear. That is more or less the concept of weak gravitational lensing. The problem, of course, is that really true? And the gravitational lensing people, of course, have known this all along. What if the galaxies are maybe aligned somehow, if they're pointing systematically, for example, along a common axis or common direction? And these intrinsic alignments, quantifying them is important to rule out that you are misled by your weak lensing inference. And, you know, there have been attempts to see this in hydrodynamical simulations. They have largely produced contradictory or null results in the past. But, you know, in Millennium TNG, we had now so good statistics and so high quality calculation that we could detect the shear galaxy correlation with incredibly high signal to noise that you see here. This is based on measurement in orange for elliptical galaxies. And you see here the statistical error bars. They are far away from zero, right? So we detect this with very high signal to noise out to 100 megaparsec. That is very important for developing a better theoretical understanding of what weak gravitational, what intrinsic alignments do to the weak gravitational lensing signal. Yeah, I don't want to go further into the details of this. This was also a major surprise, and it actually, you know, showed that certain theories for so-called quadratic tidal talking model for intrinsic alignment is really not worth very much. So it's very, very inaccurate and will probably be put to rest. And yeah, and so for example, Björn Malte-Schäfer in Heidelberg already developed a better theory in, you know, inspired by these Millennium TNG results. Yeah, then we make predictions for weak gravitational lensing. For example, the MAPS, that is one of the main probes also for Euclid, that you detect these weak gravitational lensing signals systematically and the correlation to galaxies. And we understand now from these simulations how this is impacted by the presence of baryons, because the simple theory cannot do this normally. You need these hydrodynamical simulations to do this. And just want to summarize this in the slide here on the top is the fractional impact on the weak lensing gravitational power spectrum. Due to, so basically, this is a comparison, first of all, between simulations that have only dark matter and full physics calculation, right? And the full physics calculations, these are the ones that go down here. And Millennium TNG, our one, is the green one here. And there are also other calculations in the literature on top. Our older TNG 300, which is this yellow one. And then there's also Horizon AGN and the Bahama simulation, which are these other three lines. Now, what you see is that on small scales, this is over here, there's a strong impact. You have to understand that if you want to use that data. And then there's also strong impact from neutrinos. This is the solid blue line. And you see that this neutrino impact is comparable in size and it has a different shape. So we need to both of these effects need to be understood such that Euclid can reach its precision goals, I think. And these simulations have shown that you really need to work on that really hard. Then maybe one final point on that is, if you read the press, there's a large excitement in the field that JWST has discovered somewhat unexpectedly very massive galaxies at a very young age in the universe. And the question is, here, for example, it's a diagram, the density of these stellar mass in these galaxies. What these researchers observed and interpreted is that this is far above all the theoretical models which are down there, right? So basically, there is a question: do we have to completely revise our ideas about how the early universe, evolved? That's really the question mark. I mean, for galaxy formation people, this is a major thing, right? So, indeed, we then looked at our simulations, and some of the data points at this redshift 15 we cannot explain with our calculations. So, question, right? What's wrong here? And maybe our models are wrong. Maybe the data is overinterpreted. Actually, the verdict is out on that, right? It could also be that our simulations are simply wrong at this time, because maybe galaxy formation physics proceeds quite differently at this early time. There's no guarantee that our simple models that work in the present day universe also work at this early time. And I think actually this is the explanation I favor. Now, before coming to some concluding remarks, just that you don't get me wrong, I showed you a few successes, right? So I could actually, I could have gone on a lot about successes. Also, I showed you a few tensions. I could also go on about tensions, but actually the balance sheet is quite amazing in the sense that we have a backbone theory for galaxy formation, I would say, right? So question is, which you then might ask, do we then understand galaxy formation now? And is there anything left to do? We don't understand it, and actually there's a whole lot left to do, right? Of course, how could I say anything different, of course, being a pundit in galaxy formation? But it's true. We have, we have nice images. This is a simulated galaxy on the lower right. They look increasingly like real galaxies. We have now even dust lanes in them. So that's great. But we actually have a lot of things that we wish to do, and and that's more for the experts, where our physical models are too primitive to be really robust, right? For example, we don't include normally radiative transfer self-consistently. We have sweeping simplifications for star formation, black hole formation, and so on. And I could go on for long on why this is all really a problem and why you should worry about this and why you should be skeptical about all the results I've shown. If you want to be a skeptic, be my guest. It's really true that we have to work a lot harder. Now, will that be possible in the near future? In principle, it would seem yes, of course. We just slack and wait until the computers get faster, then do the same thing again, right? Now, that's a bit sobering for us, however, in the field, is namely that there is really a shift, a marked transition now on what's possible for us in terms of computing. It's not the case anymore that the compute cores get faster. In fact, they get, possibly even slower, but you get more of them still. But even that has changed. And the fastest machines now, the so-called exascale computers, they are universally machines that use GPUs for their main computational work. This is Frontier, currently the first exascale computer in the US. In Europe, we have exactly the same machine, LumiG, same architecture, but only 1/3 of the size. But next year we'll get in Germany a machine that also have an exascale performance. But these machines are very difficult to program and use because of their heterogeneous nature. They have, much of their performance comes out of this very complicated GPU system that's connected to a host computer, but this one doesn't have that much power. And you still have to connect all of these nodes and do a calculation, spread it on many shoulders to use these level of concurrency, right? Each of these GPUs actually can do 56,000 calculations in parallel, in principle. But you have to expose this level of parallelism somehow in your calculation. Unfortunately, we do things that are tightly coupled in the universe. The gravity, for example, is tightly coupled. So it's not so clear that right away that we can use such architectures in the way, especially in the way we used to work in the field. And that's now promised my last slide. No, because I often like to compare, our simulation codes that we put on supercomputers to the way observational astronomy works, where you have a large telescope and you develop very complicated instruments that then enable the actual observations and the scientific discoveries and detections. And that's, a telescope without the instrument would be worthless. And it's similar with a supercomputer. You need the software, of course, right, to do this. And the software, however, gets increasingly complex. While I was mentioned by Fabian, I worked in my thesis on the gadget code, had 8,000 lines of code. I was very proud on this when I finished my thesis. It was great. Then, it became 2005 Gadget 2. It had already 18,000 lines. 2010, when we changed this code to a repo, had 160,000 lines. For Elastis-TNG, we had 332,000 lines, 2018. We're now currently working on a repo 2, which has 480,000 lines of code. Now, it's impossible for a single graduate student to see even through these 480,000 lines a year. Even if they work day and night, they couldn't, right? So it's not something that a graduate student can work out themselves. So that's really a problem. Yet, this hasn't really been appreciated in the field. We're still, people in my age, my colleagues, I tell graduate students, hey, why don't you write a code that is better than a repo 2? And, be my guest. So and there is, of course, no systematic funding for this at all, right? So this is all supposed to become for free. And, I think it's the same. It's a bit like we apply for time on a supercomputer, but of course we have to bring our own code, and we don't get any money to develop this code, right? This is a bit like if you applied for observation time on a telescope and we're asked to bring your own instrument, right? But this is how we operate large supercomputers in astronomy still. Okay, so I'm at the end of my talk. So I've tried to give you a bit of maybe a bit too mixed impression of how we work on simulation of galaxy formation in the leading cosmological model, lambda CDM. And these calculations are quite successful. They have, I think, advanced the understanding of galaxy formation quite substantially from the theoretical side and helped us to interpret observation data. And currently, we have JWST is a new frontier, very exciting for us. And there will be more simulation in the future trying to make sense of that. Millennium TNG, I gave you a bit of a flavor of the cosmological side of things. Maybe trying to reach 1% predictive accuracy. That's really what's needed to eventually constrain dark energy. So thanks a lot.